A balanced chemical equation can help us figure out amounts of reactants and products. And so we can use this reaction or this equation for the combustion of octane to approximate how much CO2 is being generated from our combustion of fossil fuels. In this chemical equation, 2 molecules of octane, C8H18, react with 25 molecules of oxygen and produce 16 molecules of CO2 and 18 molecules of H2O. Now, molecule is a unit that is so small that it's not useful, and so we tend to talk in terms of moles. The chemist doesn't. 6.022 times 10 to the 23rd things. And just like you could say this in dozens, 2 dozen of this would produce 16 dozen of that, because dozen is a counting number. Mole is also a counting number. And so we can interpret this as 2 moles of octane would produce 16 moles of CO2. So the coefficients in the chemical equations specify relative amounts in moles of each substance. And this is very, very useful. It might make the math simpler if it was in grams, but it just doesn't work out that way. So the amount of each substance used and made is related to the amounts of the other substances used and made. Law of conservation of mass says we can't create or destroy matter. So the mass we start with is the mass we end up with. When we balance equations, we do so by balancing the atoms, because that's what is happening in the reaction. Individual molecules and atoms are reacting in particular ratios. So when we study the relationship between quantities in chemical reactions, this is called stoichiometry. So that's a word that you'll hear a lot. I'm not going to make you spell it on an exam or anything crazy like that. So let's think about making pizza instead of global warming. Here is a recipe for pizza, very simplistic, written as a chemical equation. So 1 crust plus 5 ounces of tomato sauce plus 2 cups of cheese would make 1 cheese pizza, right? The amount of pizzas that we can make is going to depend on how much ingredients we have, right? And the relationship is given by the recipe or by this chemical equation. So there's 1 crust for every 5 ounces of sauce, for every 2 cups of cheese, for every 1 pizza. There are ratios in this recipe. And we can use these ratios to figure out how many pizzas could we make if we had 10 cups of cheese. Now, many of you can look at that and just say, well, 5, duh. The reason for using the pizza analogy is because we're going to look at how do we get these relationships from this thing that we're familiar with. So we can see how it works, and then we can apply it to things that are very, strange, like combustion of octane. So this comes down to dimensional analysis again. So here we have a given amount. We have 10 cups of cheese, and we're trying to figure out how many pizzas. So the path here is cups of cheese to pizzas. And we can do that in one step because this equation tells us that we need 2 cups of cheese for every 1 pizza. So we can just write down 10 cups of cheese. I'm just going to say 10 cups. And then we want to put pizzas on top and cups of cheese on the bottom to make the units work out. Then we need this relationship. This relationship comes from the recipe or the equation. We'll get 1 pizza for every 2 cups of cheese. So 1 pizza for every 2 cups of cheese. And now our equation is telling us that we take 10 times 1 divided by 2, and we get 5 pizzas. Any questions? You should be able to write this out. I know you can do that in your head, but you need to be able to write it down. The ratios of coefficients and balanced chemical equations give us the same sort of information. They give us conversion factors between amounts in moles of any two reactants or products. And so we can connect any two things in one step. So if we burn 22.0 moles of octane, how many moles of CO2 would form? This chemical equation gives us the relationship. From 2 moles of octane, we would get 16 moles of CO2. So we can approach this just like we did with the cheese and pizza question. We're starting with moles of octane, and we want to find moles of CO2. The balanced chemical equation gives us the relationship between moles, so we can do this in one step. So 22.0 moles of C8, H18. I have one arrow, I need one conversion factor. Moles of CO2 is in the numerator, moles of octane in the denominator. So the units work out. For this conversion factor, I just look at the coefficients here. There's 2 moles of octane for 16 moles of CO2. So 16 goes in front of CO2 and 2 goes in front of octane. Now, could you simplify that? Yeah. Is it really going to save you any time? No, and sometimes when we simplify things like that, we screw up. So I would rather just multiply by 16 and divide by 2. So I got 22 times 16 divided by 2. And the calculator is telling me 176 moles of CO2. So for significant figures, these coefficients in the balanced chemical equation are exact numbers because they come from the interactions of individual particles. And so like counting 7 pennies has no uncertainty. There is no uncertainty. 2 molecules of this produce exactly 16 molecules of that. So 2 moles produce exactly 16 moles. So we just ignore those when we talk about significant figures. Our starting number had 3 significant figures. The calculator answer had 3, and so it's all good. Any questions? Well, moles are nice, but we can't measure moles. We measure things in grams or kilograms. So we need to add a step on each end of our path here. So the last example we just did, we had an amount of A in moles and we found the amount of B in moles. And so this is the mole to mole conversion. This is in the middle of every stoichiometry problem. Moles in the middle. Often we will start with a mass of one substance and want to know the mass of another substance. So we convert mass of A to amount of A in moles. Then we can go to moles of B using the coefficients, and then we go to mass of B. The mass to mole conversions are the molar masses of the substances. So this is the general path. We will see that there are variations on this path, but this is the basic path. And so I think of this as grams to moles to moles to grams. And you just kind of chant this over and over to yourself, grams to moles to moles to grams. And you know you've got it when you wake up in the middle of the night muttering grams to moles to moles to grams. Right? It comes into your dreams. Then you've been thinking about it enough. So let's see how this works. And we're going to apply this to that greenhouse gas issue. According to the U.S. Department of Energy, the world burned 3.3 times 10 to the 10th barrels of petroleum in 2013, the equivalent of approximately 3.7 times 10 to the 15th grams of gasoline. It's a lot of gas. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. Now, is this going to give us a very, very precise number? No. This is an approximation. There are a lot of approximations put together here. So we have 3.3 times 10 to the 10th barrels of petroleum. So do we know that number exactly? No. The way this is expressed, it has two significant figures. So there's a great deal of uncertainty in that. It's plus or minus 1 times 10 to the 9th, which million, billion, what is that, a trillion? Plus or minus a trillion, you know. And then equating barrels of petroleum to grams of gasoline, well, that's assuming that all of the petroleum would be converted to gasoline, but it was not. Some of it was used for other purposes. And is gasoline all octane? No, it isn't. But this is a good representation of how much CO2 would be emitted. So there's a lot of approximations here. We're dealing with some ballpark numbers. So here we have our balanced chemical equation. And what I like to do is use the equation to organize the information that's given in the problem. So I'm given an amount of gasoline. We're going to assume that that's all octane. So under the formula for octane, I'm going to write 3.7 times 10 to the 15th grams. That's our approximation. And what are we trying to find? The mass of CO2. So here's CO2. This is what I'm trying to find. So I'm going to write question mark grams, because I'm looking for a mass there. This helps me to identify what's given and what's wanted. And then I need a path. I'm going to put the path up here on the top. We're starting with grams of C8H18. We're going to end up with grams of CO2. Do we know a relationship between grams of octane and grams of CO2? No. This equation gives us a relationship between moles. So we need the moles in the middle. Grams to moles to moles to grams. So grams of octane to moles of octane to moles of CO2 to grams of CO2. So grams to moles to moles to grams. That's the path. Once I have that path, then I'm just going to follow it like we did in chapter 1, I think, where we learned dimensional analysis. We're going to write it down. There's 3 arrows. There's going to be 3 fractions. Tells us where to put the units. So I've got 3.7 times 10 to the 15th grams C8H18. It is important to write the chemical formulas here. And times and a line. So the unit there is going to be moles of octane times and a line. And the next unit is going to be moles of CO2. And then the final arrow is going to give me grams of CO2. Grams to moles to moles to grams. Grams to moles to moles to grams. I'm going to write the previous unit in the denominator so that those units cancel out. I want grams of C8H18 to go away. And then I want moles to go away. And then I want moles of CO2 to go away. Now I'm going to put numbers in. So this one in the middle, the mole to mole ratio, is really easy. We just look at the balanced chemical equation. So there's a 2 in front of octane and a 16 in front of CO2. And so we write a 2 in front of octane and a 16 in front of CO2. The first ratio, conversion factor, and the second one are molar masses, and we've learned how to do that. So for octane, we have to calculate the molar mass. There's 8 carbons, 12.01, 18 hydrogens, 114.224. So you could round that to 114.2, or you can write the whole thing. It's not going to hurt anything. Because we're starting with two significant figures, and we're going to end up with two significant figures. So 1 mole of octane weighs 114.2 grams. We have to calculate the molar mass of CO2. To save time, I'll just tell you that's 14.01. And now we can take this 3.7 EE15 divided by 114.2 times 16 divided by 2 times 44.01. So two significance figures, that's 1.1 times 10 to the 16th grams of CO2. Any questions? So that's our estimate of how much CO2 was put into the atmosphere in 2013 through combustion of fossil fuels. How does that compare to volcanoes? Well, volcanoes produce about 2 times 10 to the 14th grams. That's also an approximation. That has one significant figure, because it's not something that we can measure exactly. So both of those are really, really big numbers, right? Are they the same? It's a little hard to look at them, right? Because 10 to the 14, 10 to the 16. I think I have on this slide. Yeah. Let's compare the result. Well, the petroleum combustion is larger, right? So let's see how many times larger. 1.1 times 10 to the 16th grams divided by 2 times 10 to the 14th grams. $55. So human combustion of petroleum products generates 55 times more CO2 than our estimate of volcanic action. So that suggests that our use of fossil fuels is probably a significant source of CO2 in the atmosphere. Now, does that prove that we are causing global warming? No. Does it suggest that? It does. And we could also argue about whether a 0.7 degree change in the overall temperature of the Earth is significant or not. There are a lot of unknown things about this. The thing about numbers and data is you can twist things and argue things to show almost anything that you want. And so it's not a simple matter, and I would encourage you to be skeptical of things that you hear in the news. Not that they are all wrong, but some of them are presented by people who have very specific agendas and motivations, right? And you can't really make an accurate judgment unless you really dig in and look at the research. And I don't know about you, but I don't have time for that. So am I going to try to conserve energy? Sure. Am I going to go nuts about it? No. Any questions? Let's do another example of stoichiometry. So magnesium hydroxide is the active ingredient in milk of magnesia. It neutralizes stomach acid, which is primarily hydrochloric acid, according to this reaction. So the question is, what mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? So there's a bunch of words in this problem. We want to focus on the numbers. So we always need a balanced chemical equation. So there's our balanced chemical equation. And I'm going to use that to organize the information here. I'm given one number, 3.26 grams of this stuff. So I'm going to write that under that formula. So I have 3.26 grams of this. And then I'm going to look for the question, what mass of HCl in grams? So here is the HCl. So there's my question, what mass in grams? That helps me to know where I'm starting, where I'm ending up. In the previous example, we started with a reactant, we ended with a product. Here, they're both products. They could be both reactants. They're both reactants. They could both be products. We could start with a product and end with a reactant. Any combination is possible. So we're going to do grams to moles to moles to grams. So it's grams of the thing we're given the mass of. So grams of magnesium hydroxide to moles of magnesium hydroxide to moles of the thing we want to know about, the HCl, to grams of HCl. When you first start doing this, you should write this path out. Once you get the hang of it, you don't have to write that out anymore. You can just sort of think it. So I've got my path. Now I'm going to write out my equation. Units first. So here's my magnesium hydroxide. There are 3 arrows, so I have 3 factors. So first will be moles of magnesium hydroxide, and then moles of HCl, and then grams of HCl. So moles of HCl come down here, and moles of magnesium hydroxide, and grams. All the units. The units then tell us where to put the numbers. I always like to start with easy things, and so the thing in the middle is the easiest. These numbers I just pick out of our balanced chemical equation. Usually in a problem, if there are coefficients given, you can assume that it's actually balanced. If there are no coefficients, you should check it because it may or may not need to be balanced. This one is balanced for us. 1 mole of magnesium hydroxide will react with 2 moles of HCl. So 2 moles of HCl for every 1 mole of magnesium hydroxide. Then I need molar masses. So the first one, magnesium, 24.31. So there's 1 magnesium, 24.31, and that 2 applies to both the oxygen and the hydrogen. So there's 2 oxygens and 2 hydrogens. And I would encourage you to write it down like that so that you can go back and check your work, because it's very easy to make a mistake. There's lots of little things to do. So 58.326 is the mass of 1 mole of magnesium hydroxide. You know, we could get picky about rounding that to the correct number of significant figures. I look at this and say, well, it's going to be limited to 3 sig figs because of the number I was given. So I don't have to worry about rounding this because this is going to have at least 4, and so it's just maybe 1 extra digit. I'm just going to write the whole thing in because that's easier than thinking about it. And that would definitely avoid rounding errors. Then over here, we need the molar mass for HCl. So that's going to be hydrogen plus chlorine. So that's going to be 36.458. Again, let's not worry about exactly how many sig figs that has because it's got plenty. So 3.26 divided by 58.326 times 2 divided by 1 times 36.458 equals 4.07. There's 3 significant figures. Write down 2 more. And then I can round this and say, well, it's 4.08 grams of HCl would be neutralized. Is anybody following along on their calculator? Did I do it right? Okay. Because I screw up pretty regularly. Any questions? This is a really, really important kind of calculation in chemistry. We do a lot of these mass to mass conversions, and then we're also going to do variations on this. And so if you don't have this one down, then when we vary the beginning and the end, it's going to get ugly. Let's do another one. Component of acid rain is nitric acid, which forms when NO2, which is also a pollutant, reacts with oxygen and water according to this simplified equation. So NO2 reacts with oxygen and forms nitric acid. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. Assuming that there's adequate oxygen and water, what mass of nitric acid in kilograms can form from this amount of NO2 pollutant? There are a lot of words in there. There's a story, right? Background information. What we need are the numbers and the units. So this is telling me 16 kilograms of NO2. So I'm going to write that under NO2. 16 kilograms. Then the question is, what mass of HNO3 in kilograms? So my question is about the HNO3, and the unit is kilogram. So we're starting with a mass, we're ending with a mass. So grams to moles to moles to grams, right? So grams of NO2 to moles of NO2 to moles of HNO3 to grams of HNO3. Oops. Was I given grams? No, I was given kilograms. Could I convert kilograms to grams? Sure I could. There are a couple of different ways you can do this problem. You can take the kilograms, convert to grams, go through this, take the grams, convert back to kilograms. That is entirely valid. But I'm going to show you something that's sort of a shortcut. Because kilo is a prefix that means times 10 to the third, right? So it just changes the size of the unit. So I'm going to treat kilo sort of as its own unit, and I'm just going to let it sit there. So I'm going to start here with 16 kilograms, kilograms of NO2. And I put the kilo in red just to sort of highlight it. I'm just going to let it sit there. So I'm going to pretend that the red thing doesn't exist for now, and I'm just going to go grams to moles to moles to grams. So grams of NO2 to moles of NO2 to moles of nitric acid to grams of nitric acid. And this would be moles of HNO3 down here, and moles of NO2, and grams of NO2. I'm just going to let that little red kilo sit there. Well, mole ratios here. 4 moles of NO2 produce 4 moles of HNO3. So it's 4 and 4. I need the molar mass of NO2, so I need to calculate that. So it's nitrogen plus 2 oxygens. So 46.01. So 1 mole of NO2 weighs 46.01 grams. And then I also need the molar mass of HNO3, 1.008 plus 14.01 plus 3 times 16. $63.018. So my last term here, 63.018 grams of nitric acid for every mole. Okay, so let's look at the units real quick here. I canceled out grams of NO2 with grams of NO2. I did not cancel the kilo. It's still sitting there. I canceled all these other units. I end up with grams of HNO3. I still have the kilo. So the unit I end up with here is kilograms of HNO3. So let's do the math. 16 divided by 46.02, 0.01, times 4 divided by 4, times 63.018. My starting number had 2 significant figures. Nothing else has less than that, so I'm going to end up with 2 sig figs. So there's my 2 sig figs, write down 2 extras. This is and so I would say 22 kilograms of nitric acid. Exactly how you do this is up to you. You figure out what makes the most sense for you, what's easiest for you to remember. Some people really like taking these little elegant shortcuts, and other people say, that confuses me. So it is entirely fine to start with kilograms of NO2, convert to grams of NO2, and then at the end convert back to kilograms of HNO3. When you do that and stand back and look at it, you'll see that this conversion from kilograms to grams cancels the gram to kilogram conversion at the other end. But in the in the fable of the tortoise and the hare, the tortoise always wins, right? Slow and steady. He just keeps going. So this is the tortoise method. It works. Any questions?